Hi, join me as I dive into the mysteries of black holes and try to figure out what's their real secret. Black holes are one of the most mind bending and mysterious phenomena in the universe. These cosmic monsters are so dense and have such a strong gravitational pull that nothing, not even light, can escape once it gets too close. But how does that happen? What's really going on at the heart of these gravitational giants? That is what we'll try to uncover in this episode of the astronomy class. So, without any further ado, let's begin. Soon after Einstein published his general theory of relativity, Carl Schwarzschild worked out the solution for the curvature of space-time around a point mass. He found that there is a critical radius at which a singularity occurs. A singularity is a place where some quantity is infinite. Very naively, a singularity can be imagined as a point of infinite density and zero volume. This critical radius is called the Schwarzschild radius. For a mass m, this radius denoted by Rs is given as 2gm by c square. But real objects are not point-like. They have some finite extent. So one interpretation of the Schwarzschild radius result is that if any object is completely contained within this radius, a singularity will occur. The significance of this critical radius can be understood from the concept of gravitational redshift. We know that if a photon is emitted at a wavelength lambda 1 at a distance r1 from a mass m and is detected at r2, its wavelength lambda 2 will be given by this expression. So, if we set r1 as the Schwarzschild radius, we find that lambda 2 is infinite even if it is only slightly larger than r1. This means that no electromagnetic energy can escape from within the Schwarzschild radius. This object contained within the Schwarzschild radius is therefore known as a black hole. Since the Schwarzschild radius varies linearly with mass and has a value of 3 kilometers for a 1 solar mass object, we can write an expression for the Schwarzschild radius for an object of any mass as 3 kilometers into mass given in solar masses. Remember that every object has a Schwarzschild radius, but it is a black hole only if the object is completely contained within this radius. For example, the Sun is much larger than 3 kilometers, so it is not a black hole. The density of a 1 solar mass black hole is pretty high at almost 10 to the power 17 grams per centimeter cube. It is higher than the density of the nucleus of an atom. However, as we consider more massive black holes, the density decreases. This strange effect happens because the radius is proportional to the mass, but the volume is proportional to the cube of the radius, and therefore the cube of mass. This means that the density is proportional to 1 over m square. Since we know the density for a 1 solar mass black hole, we can now write the density for any other mass black hole as given by this expression. By the time the mass of a black hole reaches 100 million solar masses, the density is only a few grams per cubic centimeter, which is just a few times the density of water. One should expect the region just outside a black hole to be characterized by a large change in gravitational force over a small distance. But as we discussed in our earlier video on the moon, the changing gravitational force exerted by the sun and moon on either side of the earth result in tides. And as an extension, we refer to any effect of the variation of gravitational force as tidal effects. Near a black hole, the gravitational force should fall off very quickly with small changes in distance from the surface. Now, we write the acceleration due to gravity as a function of radius as this expression, where g of r is gm by r square. So, differentiating with respect to r gives dg by dr equals minus 2gm by r square, which means that even though the gravitational force falls off as 1 by r square, the tidal effects fall off as 1 by r cube, meaning that it is most important for smaller values of r or small black holes. The tidal force dg by dr is proportional to m over r cube, just like density. Therefore, the tidal force will be less for the more massive black holes. Have you ever wondered how it will feel to fall into a black hole? Well, let's consider two astronauts, one approaching the black hole and the other staying a safe distance away from it. Assuming that the astronaut approaching the black hole can send out signals in all directions, including back to the other astronaut. As the first astronaut approaches the black hole, the distant astronaut would notice that the redshift of the signal received by him is changing. The magnitude of the redshift increases as the first astronaut becomes closer to the Schwarzschild radius. Before the Schwarzschild radius is reached, another effect becomes noticeable. The paths of photons sent out by the first astronaut are no longer straight lines. They bend. The only direction in which the astronaut can aim a beam and not have it bent is straight up. If the beam is not aimed sufficiently close to the vertical, the bending is so great that the light will not escape. Only light aimed into a cone around the vertical, which is called the exit cone, can escape. As the first astronaut moves closer to Schwarzschild radius, the exit cone becomes smaller. At a distance equal to 1.5 times the Schwarzschild radius, photons aimed horizontally go into orbit around the black hole. The sphere of orbiting photons is called the photon sphere. This means if you were to look straight out along the horizon, you will actually see the back of your head. The second astronaut never actually sees the first astronaut reach the Schwarzschild radius. The gravitational time dilation, which we'll just discuss in a minute, is so great that as the Schwarzschild radius is approached, the second astronaut thinks that it takes the first astronaut an infinite amount of time to reach the Schwarzschild radius. The time dilation makes the first astronaut appears to slow down as the Schwarzschild radius is approached. But from the point of view of the first astronaut, nothing such is happening. The Schwarzschild radius is reached very quickly, and if the black hole is of sufficiently small mass, the tidal forces will actually tear apart the astronaut. But if the black hole is sufficiently massive, the tidal forces might be survived and the astronaut will cross the Schwarzschild radius. When this happens, it is said that the astronaut has crossed the event horizon. If the black hole is very massive, the astronaut might not even notice anything unusual, except that escape is inevitable. Once inside the black hole, the inevitable journey to the center of the black hole continues. The gravitational time dilation is so great that time passes very slowly. Outside the black hole, the time rushes on while distance is covered slowly. It is almost like after crossing the event horizon, the roles of the space and time have interchanged. Meanwhile, the second astronaut can tell nothing about what is going on inside the black hole. In fact, the only properties of a black hole that can be deduced are mass, radius, electric charge, and angular momentum. By the way, in this case, we have assumed a zero angular momentum for the black hole because rotating black holes behave slightly differently. And we leave that discussion for a future episode. To understand the concept of time dilation, one must realize that simultaneity is not absolute. For instance, if we consider a clock made up of two mirrors separated by a distance L and a light beam bouncing back and forth between them, the time counting can be done by measuring the number of times the light bounces between the mirrors. The time it takes for the light beam to make one round trip is given as 2L by c. But in the frame of reference in which the clock is moving, the light beam will take a longer path as shown in the image on the right. Since the speed of light is the same in both frames, the beam must take longer to make the round trip. From the figures, we can see that the time taken for the distance to be traveled is given by 2 by c into square root of L square plus Vt by 2 squared. This leads to the conclusion that the time interval measured in the frame in which the clock is moving is greater than that measured in the rest frame of the clock. This is a very significant result because it implies that if we have two identical clocks such that one is kept at rest with respect to the observer and the other one is moving, the latter appears to run slow. It is critical to realize that the situation is perfectly symmetric because an observer who is traveling with the other clock will actually see the one at rest moving slowly. This effect is called time dilation. The amount of time dilation depends on the quantity square root of 1 over 1 minus v by c squared, which is generally denoted as gamma. This graph shows gamma plotted as a function of the ratio of the velocity with respect to the velocity of light. Note that this quantity is close to unity for small values of velocity v and attain appreciable values only when the velocity v is comparable to the velocity of light. This confirms why we don't observe time dilation in familiar everyday results where speeds are much smaller than the velocity of light. Time dilation is not an artifact of the light clock that we have discussed, but applies to all clocks. For instance, the decay of unstable elementary particles. Particles which move close to the speed of light should appear to live longer than the same particles at rest. This is tested daily in particle accelerators around the world. A dramatic example of the effect of time dilation is observed in the cosmic rays, which contain unstable particles which can decay as they pass through the atmosphere of the Earth. If the flux of cosmic rays is measured at high altitude and near the ground, we find that many more survive this trip than expected unless we account for the effect of time dilation. Time dilation also applies to biological clocks. A person traveling at a high speed will not age as fast as a person at rest. Of course, the situation must be symmetric. Each person will see the other age slower. This puzzle is known as the twin paradox. Imagine two twins are on Earth. One is an astronaut who goes on a trip at high speeds close to the velocity of light while the other stays on the Earth. From the point of view of the one on the Earth, the astronaut is moving and will not age as fast as the one on Earth. The astronaut will appear younger upon returning. Meanwhile, the astronaut sees the twin on the Earth moving away at high speed and therefore will appear younger to the astronaut. It is all right for two moving observers to see each other's age slower, but we have a problem if we try to bring the twins together both at rest. We can see which one is really younger and decide which one was really moving. Now, this violates Einstein's postulate that there is no experiment which can be performed to test which inertial frame is moving and which is at rest. That is, there is no preferred inertial frame. However, if the twins start and end together at rest, then one twin must accelerate to get very high speeds. That acceleration produces pseudo forces which can be felt by only one twin. This breaks the symmetry of the problem without any logical contradiction. A stellar black hole will not be visible even in front of a bright background because of its tiny size. So the only way to detect a stellar black hole would be through its impact on its companion or neighboring stars, which we discussed in an earlier video on binaries, a link to which is provided in the description below. But besides stellar black holes, there also exist non-stellar black holes. We have already discussed the supermassive black holes weighing several millions of solar masses believed to be present at the center of all large galaxies in our discussion on the active galactic nuclei. Do watch those episodes in case you missed them earlier. But there is a very interesting class of black holes believed to exist in between these two extremes. These are the mini black holes with masses a few times the mass of the Sun. It is believed that they may have formed when the density of the universe was much higher than it is right now, and some even believe that they may still exist. The British physicist Stephen Hawking put forward a theory in the 1970s suggesting a mechanism by which the mini black holes could actually evaporate. Hawking studied the relationship between gravity and quantum mechanics and proposed a quantum mechanical process by which this is possible. This mechanism involves a different concept of vacuum than what we are accustomed to seeing. In classical physics, vacuum simply means nothing. But in quantum mechanics, it is possible to make something out of nothing as long as you don't do it for a long time. This basically means that you borrow energy for a brief time interval, and the more energy you borrow, the less time you can borrow it for. At its core, this is related to the uncertainty principle, which involves the momentum and position of a body. So consequently, it is related to the energy and the lifetime of an energy state. In this context, it means that if a state has a lifetime delta t, then the energy of that state is uncertain by an amount delta E, and therefore the uncertainty principle can be written as delta E into delta t greater than or equal to h by 2 pi. The longer lived a state is, the more accurately its energy can be determined. Since the energy of a state is uncertain by delta E, it is possible to have the extra amount of energy and not detect it. As a result of the uncertainty principle, the quantum mechanical vacuum is a very busy place. At any point, it is possible to create a particle-antiparticle pair which requires an energy equal to mc square, where m is the mass of the particle and c is the velocity of light. The pair can exist for at most a time h by 2 pi into mc square. Before this time is over, the particles must find each other and annihilate. Electrons have masses much less than protons, and therefore the electron-positron pair will live longer than a proton-antiproton pair. We can therefore think of vacuum as being made up of continuously appearing and disappearing electron-positron pairs, along with a small contribution from heavier particle-antiparticle pairs. This phenomena is known as vacuum polarization. When an electron-positron pair is created just outside a black hole and one of the particles is pulled into the black hole before the two can recombine, the other particle will continue moving away from the black hole, and therefore the two will never recombine. The particles will then exist for much longer than the time limit due to the violation of the law of conservation of energy. But this energy must be made up from somewhere. The particles emitted from the black hole are referred to as the Hawking radiation. The process actually reduces the mass of the black hole and it will shrink slightly. For mini black holes, this energy can be a significant fraction of the mass of the black hole, and eventually the mini black hole will shrink to the point where it disappears in a small burst of gamma radiation. So in this theory, the more massive a black hole is to begin with, the longer it will live. An estimate for the lifetime of a black hole of mass m is 10 to the power minus 26 seconds into m cube, where m is measured in grams. This implies that a black hole which is 10 to the power 14 grams would have a lifetime of about 10 billion years, a little less than the age of the universe. This means that in the lifetime of the universe, black holes smaller than this mass should have disappeared. Some physicists have also suggested that when this happens, we should be able to see them as gamma ray bursts. I hope you got some clarity about what is going on inside the black holes, the concept of time dilation, and the Hawking radiation through this short discussion. What did you find most fascinating about black holes? Let me know in the comment section below. Also, let me know what other topics you would like to be covered on this channel, and if you enjoy our content, do share it with other astronomy enthusiasts. Please like, share, and subscribe to our channel because that is the only way for us to know that you appreciate our efforts. I will see you next week. Until then, take care.